In this video, we are going to study linear differential equations with constant coefficients. By differential equations, we understand equations involving differentials or derivatives. Here we shall study differential equations whose right hand side is 0 and those whose right hand side is a function of x. These differential equations are called linear because the power of each of these differentials is 1. By constant coefficients, we mean the coefficients of the differentials in these differential equations are constants. The method of solving these differential equations depends upon the nature of the right hand side, whether it is 0 or a function of x. We will study how to solve these differential equations with constant coefficients. Hello friends, you are watching YouTube channel Number Collage. This channel features videos on mathematical concepts. Effort has been made to explore the concepts through basic mathematical ideas. Hope you will like my effort. Consider a linear differential equation with constant coefficient whose right hand side is 0. In this linear differential equation, right hand side is 0. We will denote dy by dx equals d2y upon dx square equals d square, d cube y upon dx cube equals d cube, etc. Then this differential equation will become d cube minus 6d square plus 11d minus 6y equals 0. Here d cube minus 6d square plus 11d minus 6 is a polynomial function in d, so we denote d cube minus 6d square plus 11d minus 6 equals fd, which is a polynomial function in d, and write this equation 1 as fdy equals 0, which is the representation of this linear differential equation in terms of d. Linear differential equation in terms of d is, in this equation we denote this much part without y to be fd. When we put this fd equals 0, we get this polynomial equation in d, which can be solved for d. After solving this polynomial equation, we will get 3 roots because the degree of this polynomial is 3. In course of our discussion, we will see how to solve this polynomial equation. The 3 roots are d equals 1 or 2 or 3. For the first root d equals 1, we have the solution to this linear differential equation. y1 equals c1 e raised to 1x or c1 e raised to x, where c1 is an arbitrary constant. After differentiation, we get dy by dx t equals c1 e raised to x d2y upon dx square t square equals c1 e raised to x d cube y upon dx cube d cube equals c1 e raised to x. The left hand side of this differential equation will be c1 e raised to x minus 6 c1 e raised to x plus 11 c1 e raised to x minus 6 c1 e raised to x, which will be 12 c1 e raised to x minus 12 c1 e raised to x 0, which is the right hand side. Since left hand side equals right hand side, c1 e raised to 1x is a solution of given linear differential equation. For d equals 2, we write the solution y2 equals c2 e raised to 2x, where c2 is an arbitrary constant. After differentiation, dy by dx d is 2 c2 e raised to 2x d2y by dx square. D square is 4 c2 e raised to 2x d cube y upon dx cube. D cube will be 8 c2 e raised to 2x. Substituting these values, the left hand side of the linear differential equation will be 8c2 e raised to 2x minus 6 into 4c2 e raised to 2x plus 11 into 2c2 e raised to 2x minus 6c2 e raised to 2x equals 8c2 e raised to 2x minus 24 c2 e raised to 2x plus 22 c2 e raised to 2x minus 6 c2 e raised to 2x, which is 30 c2 e raised to 2x minus 30 c2 e raised to 2x. After cancelling, it will be 0, which is the right hand side. Since left hand side equals right hand side, c2 e raised to 2x is a solution of given linear differential equation. For d equals 3, solution of linear differential equation will be y3 equals c3 e raised to 3x, where c3 is another arbitrary constant. Let's verify if this solution is correct. After differentiation, dy by dx, d equals 3c3 e raised to 3x d2y upon dx square, d square will be 9c3 e raised to 3x d cube y upon dx cube, d cube will be 27c3 e raised to 3x. Substituting these values in the linear differential equation, left hand side will be 27c3 e raised to 3x minus 6 into 9c3 e raised to 3x plus 11 into 3c3 e raised to 3x minus 6 into y, which is c3 e raised to 3x. This will be 27 c3 e raised to 3x minus 54 c3 e raised to 3x plus 33 c3 e raised to 3x minus 6 c3 e raised to 3x, which is 60 c3 e raised to 3x minus 60 c3 e raised to 3x. Cancelling, we get 0, which is the right hand side. Now since left hand side equals right hand side, we have verified that 3c3 e raised to 3x is a solution of given linear differential equation. From d equals 1, we found the first solution y1 equals c1 e raised to 1x. From d equals 2, we found the second solution y2 equals c2 e raised to 2x. And from d equals 3, we found the third solution y3 equals c3 e raised to 3x. So the total solution of this linear differential equation will be y equals y1 plus y2 plus y3, that is y equals c1 e raised to x plus c2 e raised to 2x plus c3 e raised to 3x. When right hand side of the linear differential equation is 0, this solution is called complementary function. Right hand side of this LDE is 0, so we will find its solution, that is complementary function. In terms of d, this LDE will be 2d square plus 5d minus 12y equals 0. Auxiliary equation will be 2d square plus 5d minus 12 equals 0. This is a quadratic polynomial. Factors of minus 24 are plus 8 minus 3. So this will be 2d square splitting plus 5d as 8d minus 3d minus 12 equals 0. Grouping the terms, taking 2d common, d plus 4 minus 3 common, d plus 4 into 2d minus 3 equals 0. So d is minus 4 or d is 3 upon 2. So from d equals minus 4, first solution y1 will be c1 e raised to minus 4x. From d equals 3 upon 2, second solution y2 will be c2 e raised to 3 upon 2x, and the complementary function y will be y1 plus y2, which is c1 e raised to minus 4x plus c2 e raised to 3 upon 2x. In this LDE, the right hand side is 0. In terms of d, this LDE will be d raised to 4 minus 5d cube plus 5d square plus 5d minus 6y equals 0. Its auxiliary equation will be d raised to 4 minus 5d cube plus 5d square plus 5d minus 6 equals 0. This polynomial is of degree 4. Let us see how to factorize a polynomial with degree 4. First of all, write the polynomial in the descending powers of d. Here, the descending power of d is 4, 3, 2, 1 and 0. Next, check if sum of coefficients of d is 0. The coefficients are 1 minus 5 plus 5 plus 5 minus 6, which is 11 minus 11, 0. This implies d minus 1 is a factor of polynomial fd. We can verify this. For that, let us put d minus 1 equals 0. D will be 1. If we substitute d equals 1 in the auxiliary equation, we get left hand side equals 1 raised to 4 minus 5 1 cube plus 5 1 squared plus 5 into 1 minus 6, which is 1 minus 5 plus 5 plus 5 plus 5 minus 6, 11 minus 11, 0, which is right hand side. Since left hand side equals right hand side, d minus 1 is a factor of this polynomial. In order to find remaining factors of the polynomial, we will apply synthetic division. For synthetic division, the polynomial should be written in the descending powers of the variable d. In this case, it is already in the descending powers of d. Next, in a row, we write coefficients of the polynomial 1 minus 5, 5, 5 minus 6. We write value of d, which is 1 here. Then we write this 1 down here. Now this 1 multiplied by this 1 is 1 minus 5 plus 1 minus 4. 1 into minus 4 is minus 4. 5 minus 4 is 1. This 1 into this 1 is 1. 5 plus 1 is 6. 6 into 1 is 6. Minus 6 plus 6 is 0. This 0 here represents the remainder of this synthetic division, and since the remainder is 0, it implies that d minus 1 a factor of this polynomial fd. The remaining polynomial can be obtained from these coefficients. There are 4 coefficients, so the power of this polynomial will be 3. So the two factors of fd will be d minus 1 into, for this coefficient 1 we write d cube, for this coefficient minus 4 we write minus 4d square, for this coefficient 1 we write plus d, and for this coefficient 6 we write 6. So this is polynomial fd after first factorization. Next, we have to factorize this cubic polynomial. We can do this again by synthetic division. Now we have factors of this polynomial d minus 1 into d cube minus 4d square plus d plus 6 equals 0. We will find factors of this cubic polynomial again by synthetic division. But before that, let us observe that sum of coefficients of odd powers of d, which is this 1 plus this 1, is 2, and sum of coefficients of even powers of d, which is this minus 4 plus 6, equals 2. Since sum of coefficients of odd powers of d, 2, equals sum of coefficients of even powers of d, which is also 2, implies that d plus 1 is a factor of this cubic polynomial. So for synthetic division, we write d plus 1 equals 0, which gives d equals minus 1. Now for synthetic division, we write in a row coefficients 1, minus 4, 1, 6. Then we write this minus 1 here. We write this one here. Minus 1 into 1, minus 1. Minus 4, minus 1, minus 5. Minus 1 into minus 5, 5. 1 plus 5, 6. 6 into minus 1, minus 6. 6 minus 6, 0, which is remainder of this synthetic division. And since remainder is 0, the remaining coefficients 1 minus 5 plus 6 gives us the third factor. So we write the auxiliary equation d minus 1 into this d plus 1 into a quadratic polynomial from this coefficients d square minus 5d plus 6 equals 0, which is d minus 1 into d plus 1, and this quadratic polynomial can be factorized as d minus 2 into d minus 3 equals 0. So we get 4 values of d: 1, minus 1, 2 and 3. For d equals 1, y1 is c1 e raised to 1x, which is c1 e raised to x. For d equals minus 1, y2 is c2 e raised to minus x. For d equals 2, y3 is c3 e raised to 2x. And for d equals 3, y4 is c4 e raised to 3x. So the total solution or complementary function CF will be y1 plus y2 plus y3 plus y4, which is c1 e raised to x plus c2 e raised to minus x plus c3 e raised to 2x plus c4 e raised to 3x. So far we have seen how to solve linear differential equations with right hand side 0, where we can solve it by finding the complementary function only. Now we are going to see how to solve a linear differential equation whose right hand side is a function of x. For example, let us see how to solve a linear differential equation dy by dx minus 3y equals x, where this x is a function of x. Here, as usual, we have to find the complementary function by considering the auxiliary equation dy by dx minus 3 equals 0, which in terms of d is d minus 3 equals 0. d is 3, so the complementary function will be y equals c1 e raised to 3x. Now, because the right hand side of this equation is a function of x, there is another solution of this linear differential equation known as particular integral pi. During the course of our discussion, we will understand what is a particular integral and how to find it. But at this stage, let me directly tell you that the particular integral of this linear differential equation is, say, y1 is minus x upon 3 minus 1 upon 9. How did I get this? We will discuss that later on. At this stage, let us check whether this particular integral is a solution of given linear differential equation. Let us verify this. After differentiation, we get dy upon dx equals minus 1 upon 3. And after substituting this value in the given linear differential equation, we get left hand side equals, putting minus 1 upon 3 in place of dy by dx minus 3, and putting this minus x upon 3 minus 1 upon 9 in place of this y, we get minus 1 upon 3 plus x plus 1 upon 3. Minus 1 upon 3 plus 1 upon 3 will be 0, and we get x, which is the right hand side. Since left hand side equals right hand side, this particular integral is correct. So the solution of this linear differential equation whose right hand side is a function of x is not only complementary function c1 e raised to 3x but also the particular integral minus x upon 3 minus 1 upon 9. So its complete solution will be combination of complementary function and particular integral. So the complete solution is y equals c1 e raised to 3x minus x upon 3 minus 1 upon 9. Let us solve another linear differential equation whose right hand side is a function of x. d2y upon dx square minus 4 dy by dx plus 3y equals e raised to 2x. Here the right hand side e raised to 2x is a function of x. This LDE in terms of d will be d square minus 4d plus 3y equals e raised to 2x. First, we will find complementary function. For that, we shall need auxiliary equation, which is d square minus 4d plus 3 equals 0. After factorizing, d minus 1 into d minus 3 equals 0. That gives d equals 1 and d equals 3. So the complementary function will be c1 e raised to 1x plus c2 e raised to 3x. Let me tell you at this stage, particular integral of this LDE is minus e raised to 2x. How to obtain this we will discuss later on. But before that, let us verify whether this particular integral is correct. Differentiating particular integral, we get dy by dx equals minus 2 e raised to 2x, which is d, and d2y by dx square equals minus 4 e raised to 2x, which is d square. We will substitute d and d square in this LDE, whose left hand side will be minus 4 e raised to 2x in place of d square minus 4 into minus 2 e raised to 2x in place of d plus 3 and particular integral minus e raised to 2x in place of y. This will be minus 4 e raised to 2x plus 8 e raised to 2x minus 3 e raised to 2x. This will be e raised to 2x, which is right hand side. And since left hand side is right hand side, it is verified that this particular integral is correct. Now the complete solution of this LDE y equals complementary function plus particular integral, which is y equals cf c1 e raised to x plus c2 e raised to 3x plus particular integral minus e raised to 2x. So the takeaway of today's discussion so far is when the right hand side of a linear differential equation is 0, its solution consists of only complementary function. When the right hand side of a linear differential equation is a function of x, then its solution consists of a combination of complementary function and particular integral. We will discuss more about this in the second part of this series, linear differential equations with constant coefficients, part 2. If you like this video, please like it, share it, and subscribe to this channel. See you in the next video. Until then, keep watching Number Collage. Thank you.